Let's pick up with the example that we were walking last time. So our goal in the last 5 minutes-ish of class yesterday was to find all of the solutions to that degree 5 polynomial. And what did we do? We found that it'll have at most 5 roots. In fact, if we find all of the complex solutions, there should be exactly 5 complex roots, as long as we're willing to count with multiplicity. There could be 5 or 3 or 1 positive roots. There won't be any negative roots. Again, we have to count with multiplicity for Descartes' law of science to 1. We found a complete list of candidates to be rational roots, and we found 2 of them actually are x equals 1 and x equals 3. And I've gone here and done something that probably you're going to do anyway. There's a graph of this function. Does it look like those are indeed rational roots at 1 and 3? Take a look at the root at x equals 3. Does it look like it's like a linear root or a quadratic root? Quadratic. So I expect 2 factors of x minus 3 to appear here. So I know some things about how this should factor. Even if I didn't notice that about the graph, just by knowing these 2 things are roots, I should be able to take this complicated polynomial that I have, that I won't write right here. I should be able to write it as x minus 1 times x minus 3 times something. And how am I going to find that something? Well, I think I'm going to do some division. So I guess I'll give you all a choice of options right now. Should we do synthetic division or polynomial long division? Synthetic, polynomial long. All right, let's do some synthetic division. So, first of all, I see 1 is a root, so I know for a fact that x minus 1 will divide into this polynomial. To figure out how it will, well, synthetic division says that you put like a little 1 there. You put the division box, and then you put the coefficients in order. So 1, negative 7, 19, negative 47. I'm going to separate these with commas, otherwise I might get confused and think that's subtraction. 60, and 46. And I'm feeling just a little bit loopy and tired, so I suspect I may have made a mistake there. I'm just going to do a quick double check. Thank you. Okay. Any other just weird things I've done? Excellent. All right, now let's follow the synthetic division algorithm. So synthetic division says we'll take this 1 and just put it there. There's the leading term of the result of division. Now I take this 1, multiply it by 1, put it here, and do addition. Negative 7 plus 1 is negative 6. 1 minus 6. Now take that negative 6, multiply it by 1, that gives negative 6. Add those 2 things together, you get 13. So the next entry will be 13. And now just keep on going. 13 times 1 is 13. Negative 37 plus 13, 24. Okay, negative 24. Keep on going. 1 times negative 24 is negative 24. 46, right? Okay. 36, so I put a 36 there. Yeah, because that has a positive next to it. Yeah. Finally, 1 times 36 is 36. Negative 36 plus 36 is 0. And I knew this should divide in evenly, so I knew I should get a remainder term of 0. That's a convenient checksum whenever you're doing synthetic division, or any form of division. Does the result actually divide evenly in? If it doesn't, and it should, then something's wrong. So, what does this say already? This says the polynomial that you want to study, which I won't write down because it's like too big to spend the time to write down. It says that this polynomial factors as x minus 1 times 1, so there's the 0th term, 1, 2, 3, 4, degree 4 polynomial, x to the 4th minus 6x cubed plus 13x squared minus 24x plus 36. That's good. So now we have that x minus 1 factor. But I also want to get this x minus 5 factor to show up. So that means x minus 3. X minus 3 should divide evenly into one of these two factors for it to divide evenly into the whole thing. It's going to divide evenly into the big factor because it doesn't divide into x minus 1. So, same way as you would like factor a number by finding prime factors and doing long division. Spiritually the same. So, let's repeat. Let's take x minus 3 and do synthetic division. So that'll be 3. And now I need to divide it into 1, minus 6, 13, negative 24, 46. And, yeah. Nope. All right, the same way as, suppose I asked you to factor 72. You could say, well, that's like 2 times 46, right? You could also start by saying, well, 72 is 3 times 1, no, 2. You could also factor it that way. And then so either way, we get to the same point, regardless of which order we do the factoring. In fact, a thing we could do if we were willing to do long division instead of synthetic is, instead of Gesundheit, dividing these in one at a time, we could FOIL out x minus 1, x minus 3, and see how that divides using long division into the big polynomial. It would be only one step instead of 2. Downside is you'd be doing polynomial long division instead of synthetic. And you also risk forgetting that you have these two separate factors, which is important. In the time that I was stalling, how many people just already did this? Cool. Well, I'll see how people feel. Should I go through the synthetic division, or would people like to do it on their own? Should I go through the computation myself? Okay, then I'm going to stall for a little bit. And you are going to tell me in, I don't know, like a minute, what is on top of this box. What numbers are on top of the box? Yeah.
1, 2, 3, 4, 12, 15.
That agree? Cool. Should I actually do? Cool. What does that mean? That means this pink piece, which was x to the 4th minus 6x cubed plus 13x squared minus 24x plus 36, factors as x minus 3 times that thing that you just told me, x cubed minus 3x squared plus 4x plus 12. Could that be a plus 12 or a minus 12? Okay. So what conclusion do we make? We took the original polynomial p of x, we pulled out an x minus 1, and got the result of division to be this pink thing. That pink thing we can now pull an x minus 3 out of, which we want. And let's just put what we're left with. X cubed minus 3x squared plus 4x minus 12. All right. And remember, our whole goal here is to find all of the solutions to p of x equals 0. And right now, the complicated looking piece is still degree 3. Do we know how to solve degree 3 polynomials? No, well, I mean, you might, because maybe, like, you went and, between yesterday and today, you went, like, looked up what the cubic formula is and then otherwise. That'd be a bit much. And in fact, since I know this thing should factor 1, because I picked the damn thing to factor, it'll be easier to factor than using that complicated formula. So, let's keep on factoring. And here's the trouble. I've already used up the x minus 1 factor and the x minus 3 factor. But let's look back at the graph. Do I expect one of those factors to be like high multiplicity? Which one? The 1 and 3. And even if you didn't have like a graph to look at, you could just test if any of them are still factors. So let's see if x equals 3 is still a root of x cubed minus 3x squared plus 4x minus 12. So let's plug in x equals 3, see what happens. And you could do this using a calculator, but since it's just one calculation, the biggest thing happening is cubing. I bet we can do it by hand. 3 cubed is 27 minus 3 times 9. Oh, neat. 3 times 9 is 27, right? So those two will just cancel out. Plus 4 times 3, that's 12, minus 12. Oh yeah, that totals up 0. So, nice. I know that x equals 3 is a root. So, that means I should be able to do synthetic division again. 3 dividing into x cubed minus 3x squared plus 4x minus 12. Those are close enough that I'm going to separate them with commas so I don't confuse myself. So let's do synthetic division again. And you'll probably have your synthetic division done before I do. So let's see. Copy down that 1. 1 times 3 is 3. Cool. Those cancel. It becomes 0. Put a 0 there. 4 plus 0 is 4. So you put a 4 there. 3 times 4 is 12. Remainder is 0. That's good. So that tells us that this thing in this green polynomial factors as x minus 3 times x squared plus 4. So far, so good? All right. So that tells me how the whole polynomial factors. The whole polynomial, p of x, factors as x minus 1 times x minus 3 times the thing in green from above, which now I know how that factors. It factors as x minus 3 times x squared plus 4. Sorry, I went off the bottom of the screen. Cool. Easy to solve this now? Let's do it. So, I know that x equals 1 is a root. I know that x equals 3 is a root, and it's a root of multiplicity. The problem doesn't ask for the multiplicities of the roots, but that's okay, we can find the multiplicities anyway. So that's from the x minus 1, the x minus 3, and the x minus 3. X squared plus 4, what are the solutions to that? Sorry, x squared plus 4. I think I may have said minus. Well, let's do it. X squared plus 4 equals 0. I want to solve that. What should I do? How do people default to the quadratic formula? Yeah, like you can, but I want to be lazier than that. This is easier to solve than using the quadratic formula, because there's no x form. So instead I'll just subtract the 4 to the other side. I see a negative under a square root. That means that the solution's not going to be real. But I kind of knew that already by looking at the graph. Does it look like this has any solutions other than those ones that we already have? So the other solutions, because there should be 2 other solutions, just won't be real. And what is this as a complex number? Plus or minus 2y. All right. X equal to 2i and x equal to minus 2i. And maybe as a quick just like check, let's see if this agrees with our intuition. It was a degree 5 polynomial. Did we find 5 roots as long as we count multiplicity? We said there should be 5 or 3 or 1 positive roots as long as we count up to multiplicity. How many positive roots are there? 3, as long as you're willing to count multiplicity, which you have to use Descartes' law of signs to be true. No negative roots. There were no negative roots. Cool. I think we know how to solve high-degree polynomials, at least in the special circumstance that this algorithm actually works. I like it. The first thing we needed there to exist were the rational roots of this polynomial. If it doesn't have those, then this algorithm kind of stops very early on. Cool. Looks feel pretty good. Think you could do a similar problem if, say, it's homework? Cool. Take a look at that homework. Maybe have some questions for me about it on tomorrow or Monday or something. Because the homework is like basically the same page again, but with a different starting polynomial. I think I may have liked it to be like slightly simpler in that it has like all real roots. Not that that makes a huge difference. Anyway. Right, we're all comfortable walking with complex numbers at this point, so. Let's start in on one new chapter. Maybe this is a good time to say this. So yesterday I handed out this review packet for that midterm that's next week. I think this will be a week from today on the nose. At this point, you have all of the material that will be covered on that midterm. I'll give you an extra week to think about it. I'm sure there are no surprises. Any people take the time to look at that review document yet? Okay, then I guess I can't ask you if you have any big questions about it. That's totally fair. Like, you've only had it for a day. Rational functions. So, rational functions are not a huge step up when just studying polynomials. But it's a big enough step up that it'll give us more things that we can do with these functions, more things we can model. So here are some functions just to build up intuition. Let's play the game of are these or are they not polynomials? 5, is that a polynomial? Folks for yes? Anyone for no? Excellent, constant functions are polynomials. Next one, 1 over x. 1 over x, polynomial or not polynomial? Polynomial? Not polynomial. Perfect, you're not allowed to divide by x in a polynomial. Next one, polynomial or not? Polynomial? Yeah, of course, it's like literally a bunch of powers of x next to numbers. Next one, polynomial or not? I just see some people saying no. Cool. You're not allowed to divide by things involving x in polynomials. Next one, polynomial or not? You could FOIL it out and get it to look something like that. So these two things in this list that want polynomials, like if I asked you to do something about those, you could probably turn them into something involving polynomials reasonably quickly. Like if I asked you to solve x plus 1 over x minus 1 equals 2, how would you do that? You'd probably start by cross-multiplying, turn that into x plus 1 equals 2x minus 1. Oh, hey, look. That's a polynomial equation. It's a linear equation. You can solve that. So these two functions, like they're not so far from being polynomials. You could probably study them by studying polynomials. We'll make up a name for that sort of function. These are rational functions. A rational function is a ratio of polynomials. Just like how a rational number is a ratio of integers. That is, anything of the form p of x divided by q of x. I guess q of x had better not be the 0 polynomial. Because right, you don't want to divide by 0. At least not everywhere. You're allowed to have functions in the denominator that is 0 somewhere. You just have some holes in the domain. It's called a rational function. All right, so let's classify each of these as rational functions or not. Is it a rational function? Is it a ratio of polynomials? Yeah, of course. Next one, x cubed plus x plus 1, is that a polynomial? Folks for yes? Anyone for no? Anyone for, I think you're trying to trick me, Chris, so I'm not going to pick one? All right. So indeed I am. Is that the same thing as what it was before? Is it now a polynomial divided by a polynomial? Yeah, that one you can think of as a polynomial. So this is a rational function. What do you think? Is every polynomial automatically a rational function? Yeah, in the same way as every whole number is also a rational number. 5 is the same as 5 over 1. Every polynomial is rational. Because you could write it as p of x, that polynomial, divided by 1. Next one. 1 over x cubed minus 1. Is it a rational function? Yes? Yeah. This is why it was important that constants be allowed to be polynomials. If a constant wasn't allowed to be a polynomial, I wouldn't be able to call that a rational function. But I'd like to call that a rational function because I can study it the same way with any other rational function. Next one, x plus x inverse. Polynomial or no, rational function or not rational function? Rational function? Not rational function? Hesitant to make an assumption? Cool. So those of you who said this is a rational function, it's not like literally polynomial divided by polynomial yet. So what, like, why is that a rational function? You could, but then you'd still have this like negative in a power. So you could write that as x plus x inverse over 1, but the top's not a polynomial yet. So what could you do instead? Yeah, that x inverse is 1 over x. So this is x plus 1 over x. What should you do when you see like a thing plus a fraction and you want to simplify? Yeah, make the denominators equal. Put a common denominator. So to do that, that would be x squared over x plus 1 over x is x squared plus 1 over x. Now is it literally a polynomial divided by a polynomial? Yeah. So that's a rational function. What about this last one? Would you want to call that a rational function? Could you do a walk similar to the walk we just did and get a common denominator and so have that be a polynomial divided by a polynomial? Yeah. Would you want to if you didn't have a good reason to? And I certainly won't because like I'm not interested in this any beyond that. So all of those things are rational functions. Maybe I'll add one more to the list just to add one more example. What about the square root of x? Is that a rational function? Can you write that as a polynomial divided by a polynomial? Any folks want to say yes? Any folks want to say no? Okay. Maybe I'll ask for intuition this way. If I ask you to take the square root of a number, can you do that by like doing addition, multiplication, subtraction, division, and that's it? You can't, right? Like square rooting is a different thing. Square rooting can't be made out of just addition, subtraction, multiplication, division. Square root is a new thing. It's not a rational function. And we'll see a few comparisons in just a little bit that I think will help convince you of that. Rational functions have very particular types of graphs. All right. So let's carry on. So, just like you would with rational numbers, if I handed you a ratio that was 2 over 4, you would say, oh, that's needlessly complicated. I'm going to rewrite that as 1/2. I don't want to do anything with it. Or you should, anyway. If you want to keep on doing things with these answers, you should simplify them. Otherwise, your life from then on will just be harder than it needs to be. Same thing with rational functions. If you see any common factors, you should cancel them. So, if you ever manage to get the numerator and denominator factored, and you find a common factor, you should cancel them. X squared times x minus 2 divided by x minus 2 times x plus 1 is x squared plus 1 divided by x plus 1. Do you think there are secretly any more common factors in there? No, x squared plus 1 doesn't factor. Its solutions are I and minus I. I guess that means it does factor if you're willing to have complex polynomials. And you know, say again? X plus 1 is that's not a thing times a thing. It's a perfect square plus 1. So it's going to be 1 bigger than a perfect square. If you do factor it, if over the complexes you could factor it as x plus I, x minus I over x plus 1. Not that that would be something you would want to do, because that makes it like harder to graph, not easier, because there are like complexes floating around. Now you don't even know that it's like a real function. It could be a complex function. But now you see there are no common factors. So, just like you would call 1/2 a rational number in a reduced form, we'll call a polynomial divided by polynomial in a reduced form if the numerator, p of x, and q of x, the denominator, have no common factorize. Cool. So, nothing fancy right there. If you have a ratio and you want to do more things with it, it might be worth checking to see if it's in reduced form yet. If it's not in reduced form, then cancel some things. Maybe I'll point out one thing. When you cancel those x minus 2's, do you make the domain bigger? I think so, because right now, if you plug in x equals 2 before you cancel, you'll get like 0 divided by 0, which isn't a thing. 0 divided by 0 does not make sense. You can't divide 0 by 0 either. Oh, but now when you plug in x equals 2, you'll get like 5 over 2, I think. So whenever you simplify, you make the domain a little bit bigger. So rational functions, you'll make the domain bigger when you simplify. That's nothing new, though. We've seen that before. All right. Carrying on, graphs of rational functions. So here's something that's not a surprise. There's the graph of 1 over x. Maybe I'll color it a little bit. Y equals 1 over x. And let's just make a quick inspection. Does that graph have any behavior that's like a bit different from what you would see just for polynomials? Yeah, there's like a really big jump in the middle. There's like a disconnect. Maybe an even easier thing to visualize from this is, can you plug x equals 0 into 1 over x? Nope, you divide by 0. Can you plug x equals 0 into any polynomial, though? Yeah, pick any polynomial. It's a bunch of like x's raised to power. 0 to a power is just 0. You'll end up just seeing constant. So 0 is in the domain of every polynomial. So let's see, 0 is not in the domain, but 0 is in the domain of any polynomial. It looks like there's like a really big jump at x equals 0. Maybe just remind ourselves of that. So here's the observation about rational functions. The graph of rational function p of x over q of x, as long as it's in reduced forms, there will be no jumps on the graph except when the denominator equals 0. The graph of a rational function p of x over q of x in reduced forms the graph of a rational function, that's grammatically bad, will have no jumps except at the zeros of q of x, where the y value on the graph will shoot up to either plus infinity or minus infinity. And we see this happening right here. The denominator of this is just x. It's only 0 as x equals 0. We see y values shooting off to infinity on the positive side and negative infinity on the negative side. That feel good? We'll just make up a name for that, and a name for that, and a little bit more behavior. So an asymptote for a curve is a line for which the distance between that line and the curve gets small as long as we look really, really far along the line. So let's just see an example of what this doesn't mean. So same thing, here's 1 over x. There's a line. If I look really far along this line, Are those points close to the graph 1 over x? No. So this is not an asymptote. What lines does this graph get really close to? The axes? Yeah, I think that looks right. If I look really, really far along the x-axis, in fact, in either direction, it looks like the graph gets super close to that. If I look along the y-axis, yeah, if I go really far up on the y-axis, the graph is getting really close to the y-axis. So its asymptotes are the axes, like you said, x equals 0 and y equals 0. When an asymptote happens to be a vertical line, we'll call it a vertical asymptote. That seems like a reasonable notation, I think. So those two asymptotes we found, which one's a vertical asymptote? The y-axis, which is given by x equals 0. I guess the other one will be a horizontal asymptote then. It has a horizontal asymptote at y equals 0. That feel pretty good? All right, so let's do a quick understanding check. There's one particular, I have a particular thing in mind with this understanding check. But here's what I'd like you to do. The results will vary. Sketch me a graph which is a horizontal asymptote at y equals 2. Y equals 2. Which has a vertical asymptote at x equals 3. And a vertical asymptote at x equals 2. So I've just drawn those lines in. Results will vary. So take a moment, sketch me such a graph. And there are like infinitely many possible examples. So I think I'll go ahead and sketch an example. This will be an example which I've chosen intending to be something that will make you upset. So I'm going to sketch this. How do people feel about that? Is there anything there that makes you upset? Oh, that's good. Because this does satisfy everything, right? Does it get really close to this horizontal line of y equals 2 when we travel far along it? Get really close to this vertical line, at least on that extreme of it. Asymptotes only have to be achieved on at least one end of them. It doesn't need to get to both ends. It gets close to both ends of this vertical asymptote. It also gets close to y equals 2 on the other side. So the reason I picked that example is because oftentimes I find that students come into this class thinking that graphs can never cross their asymptotes, their horizontal asymptotes. And they can. Graphs can cross, achieve the y value at their horizontal asymptote as often as they please. Rational functions are modeled on polynomials, and polynomials only achieve any given value finitely many times. So, like, rational functions will only hit their asymptotes finitely many times, but they only achieve any y value finitely many times, but they still can. And we'll see some explicit examples of that happening. Notice, I'm not saying that a graph has to cross its horizontal asymptote. Does 1 over x cross its horizontal asymptote? No. But you don't know that without knowing some more stuff. It's possible to happen. And we will see some examples of that happening by the time we make it to the end of this packet, which I've got 10 minutes, so that might not be today. So let's carry on. So here's the observation. A curve is permitted to cross its horizontal asymptotes. It's also permitted to not cross its horizontal asymptotes. You'll notice I said horizontal. Is there a reason that a curve can't cross its vertical asymptotes? Yeah, it has something to do with domain, but it also has, let's just try to like, there, now that thing crosses its vertical asymptote. Has some like important property of functions been violated? Yeah, what's that property? Vertical line test. So you have to have x values that get really close to that vertical line, so you can't also get y values that correspond to crossing. So you can't cross your vertical asymptotes, but that's not anything fancy. That's just the vertical line test. All right. Cool. All right. So let's read off some facts about graphs from just what the function looks like. If you have a rational function p of x over q of x in reduced form, it's going to be important that all of these be in reduced form. Let us find all the x-intercepts, and let's do this off to the side to figure out what should go there. How do you find the x-intercepts of absolutely anything? Set y equal to 0. So that means you need to know when p of x divided by q of x equals 0. And obviously we can't like solve this all the way out for x without knowing what p and q are. But something you could do to simplify it a little at least. Maybe multiply that q of x to the other side. So that would mean that p of x is q of x times 0. What's anything times 0? 0. Unless that something doesn't exist, which is kind of what this in reduced form is. That's its job. So if you want to find the x-intercepts of p of x over q of x, just set the numerator equal to 0. Similarly, to find the vertical asymptotes, as is summarized above, set the denominator equal to 0. So the numerator tells you x-intercepts. The denominator tells you horizontal asymptotes, which I will pretty consistently abbreviate as HA. And HA won't have any other jobs this class, so that won't be too ambiguous. Yeah. Yeah, it does. So that probably shouldn't be HA. That should be VA. I appreciate that. We will, by the end of this packet, discuss how to find horizontal asymptotes. These are vertical asymptotes. And let's pause for a moment and use these facts. So what if I asked you to find the x-intercepts and the vertical asymptotes of this polynomial, that rational function? Could you? Yeah, I think like pretty easily, right? Where are the x-intercepts? At x equals -1, which maybe if you want to be a huge pedant, it's at the point -1, 0. Where are the vertical positive one. And a vortical asymptote is not a point, it's a line. And this line is specified by x equals 1. Think you can do the rest? All right, maybe in the interest of time, let's talk through this one and then go down to the one that I've labeled as a trick question. So there's one, x squared minus 1 divided by x squared plus 1. X-intercept and vortical asymptotes. This one I think requires at least a little bit of thought to get either of those. So, x-intercepts first. How do you find the x-intercepts of a rational function? Numerator equals 0. Oh, actually that's not so hard, is it? Is that something that is that something that you just already know the solutions to? Yeah, what are they? Oh, we could find them. So you need to like solve that equation. One of them is 1. And negative 1. So you would add 1 to the other side. Then you would say, well, I'm going to take a square root. But whenever you undo a square with a square root, you lose plus or minus information. So it looks like the x-intercepts are at 1, 0, and negative 1, 0. All right, vortical asymptotes. How do you find vortical asymptotes? Something similar, but you set the other piece equal to 0? All right. That also look easy to solve? Yeah, tell me about its solutions. Yeah, so the two reasonable answers here would be x equals plus or minus I, or possibly just no real solutions. Both are reasonable answers in this context. So the vortical asymptote is like something graphical. And we've only been graphing real things. So the graphs we draw wouldn't see those vortical asymptotes. If you were willing to establish a convention for how to graph complex functions, which you could, right? So the complex plane has like a real component and imaginary component, so you picture the whole domain as a plane. And then maybe you would assign color values depending on what complex numbers you see at each point. If you did that, you'd see things going off to whatever color designates infinity at plus or minus I. And you can see heat maps of these things. A trick question. Let's close with that. So I've got 2 minutes. Let's do this. X squared minus 1 divided by x minus 1. Let's suppose I ask you for the x-intercepts of that. Cool. So you have fallen for the trick. So here is the wrong thing to do. Set the numerator equal to 0. You'll get x squared minus 1 equals 0, which we've just seen gives x equal to plus or minus 1. What about the vortical asymptotes? Yeah. I hear there are none. But it looks a lot like there should be, right? There's a denominator there. And just look at that. It looks like x equals 1 is a vortical asymptote. So why aren't there? Oh, that highlighter is real bad. Fortunately, it's erasable. You need to check that the sucker is in reduced form first. This was not in a reduced form. And here's a sanity check you can make at the end. This chart looks like it says that a vortical asymptote occurs at the same place as an x-intercept. You can't have 2 different behaviors at a single x value. If you get that happening, you automatically know, oh shoot, I need to just like do some factoring. So it's a mistake that's easy to make because sometimes it's hard to factor things. But if you look at the answer, that particular bad behavior will tell you you just needed to go back to the drawing board and do some factoring. Neato. And how am I doing for time? actually 3 seconds past 4. So we will pick up on this starting tomorrow, right? Today's Thursday? Okay. And what will we do next time? We'll do a little bit more graphing with the culmination of we will discuss how to find horizontal asymptotes. And if you find the mental energy, maybe take a look at the review document for the midterm. Maybe don't try to solve everything, but just look at each question long enough to say, do I know how to solve this? Because it's something you already know how to solve, and it would be like, well, it'd take me 2 minutes, but I could do it. Maybe it's not worth your time right now. Excellent. Appreciate it. Thank you.